Hi, I'm Sophie Kowalik, and this is the Lab 5 Falling Slinkies. So just to outline what I'll be going through, I'll have the purpose of this lab, some things to know like physics principles, my tracker results from the video, the coding I put to create my model, the graph of the model, and then I'll compare the tracker and coding graphs. And then I'll conclude with some human error and my main question of the lab. So the purpose is to model the motion of the stretch slinky drop from static equilibrium. And we're going to see if we're just going to track the bottom of the slinky to see if it stays stationary like the video. And then I'll compare the predicted and model graphs. So some things to know beforehand: Newton's second law, F equals ma. I'll show the different forces that act on the spring, and you can see drag, tension, and gravitational forces. We'll use the velocity and position update formulas in my coding, and then the momentum principle will also be used. So when I put it in tracker, this is how I calibrated it: 1.78 meters. The mass of the slinky was 0.218 kilograms. The initial position I got from the graph, and the velocity starts at 0. If you can see here, I tracked the center of mass only at the bottom, and that may be why this is so uneven, but I'll explain that later. Coding part 1. So for my model of the graph, I went ahead and put in my initial conditions. We have the mass, initial position and velocity vectors, gravitational acceleration. The J hat shows the direction of the spring, the unit vector, and then this is our drag force constant. So this time, 5.472 seconds, is the time up until the bottom of the slinky begins to move. But until then, it stays constant. The net force is the weight force plus the tension force from the slinky. We know the tension force is pointing up. We have the velocity update and position update formulas from the momentum principle, and that's about it. So I had to create a loop for this. Okay, so the time is 8.575 seconds, and that's just till the bottom of the slinky reaches the bottom, or reaches the ground. And then the net force is made from the weight force and the drag force. And then again, we have the velocity update and position update formulas. So this is what the model resulted in. And as we can see, it has the constant force, which is similar to how my predicted one looked. If we compare the two, this one obviously isn't as constant because of the way I track the center of mass, but you get the idea. It's pretty close. So the main question: does the bottom of the model slinky stay stationary like in the video? So if we look at these two, yes, it does, because it's constant the whole way through. Obviously, mine tracker from the video, it's a little wonky, and that's because of my potential errors, which tracking the point of mass was a little difficult because it stayed constant for so long. It was hard, and when it started to move, it was harder to see where it was going. Force is not accounted for: air force and drag force. And then some improvements would be to maybe track the bottom and top of the slinky separately, to hopefully make it more accurate and easier to calculate the center of mass.